Hello, my name is Ildar. I am a data scientist at Big Data MTS. Previously, I worked at Tinkoff Bank, and today we will talk about how to select similar groups for A/B tests and about the difficulties of small data samples. Let's go over the plan. First, we will talk about A/B testing on small data samples, then about algorithms of selecting similar groups. Then we will move on to the cases that I actually encountered while we were conducting an A/B testing for a set of geographical regions and evaluating a CRM campaign in the B2B segment. Okay, let's start. Basically, the main difficulty in A/B testing on small data samples is the group selection for the test. It could be more sophisticated if we wanted to split all available objects into fair groups by some measure. In the case of Russian regions, all regions have to be divided into two groups. Also, parametric criteria are poorly applicable. We usually have low sensitivity on small data samples, especially if we are looking at money metrics with high variance. On top of that, sometimes it is difficult to measure sensitivity and power before starting a test. Let's take a look at the full pipeline and highlight these issues on it. Well, first we choose the metric for evaluation, discuss the expected effect with the customer, then we select test, either a parametric or non-parametric test. Then goes an important part of choosing an algorithm that we will use for similar group selection. We conduct an AA test, then evaluate the correctness or false positive and look at how our p-value is distributed, closer to the uniform distribution or not. If everything is correct, we add some synthetic effect to one of the groups and estimate the power. Important to highlight, when we work with small data samples, one of the main problems is to choose the right algorithm for selecting similar groups. Also, we'll work with non-parametric tests. Let's look at available methods and try to answer the question why this is a problem at all, to make A and B groups balanced by some indicators. In other words, to make them look the same. In a particular case, stratification is just an example of when we want to make sure that the subsamples have the same class distribution as the original sample does. But we can face difficulties linked with money metrics. It can be tricky to make similar groups because of this. Also, our groups are small and the science factors by which our groups should be similar can also be some kind of money metric. As an example, consider the case when we want to split stories by profitability, regions by income, companies by profitability, and let's look at 4 algorithms that will help us to solve our problem. To begin with, I want to make a couple remarks for all methods. It is important to have some historical database on which we select similar groups and the validation sample. We conduct an AA test and test how our algorithm for selecting similar groups works on validation sample. On a historical period, we select n similar pairs of groups A and B according to our algorithm. We do this among a large set of pairs of groups, so we have n similar pairs. Then for these pairs, we run the AA test n times on a validation sample and test how our algorithm for selecting similar groups works. Thus, we also check the robustness of the algorithm. In the historical period, we want to find such pairs that have behaved the same way in the past and check on a validation sample if they will continue to behave the same way in the future. The first algorithm is based on group selection according to a homogeneity test. To start with, we select a target metric and or any other historical feature by which we want to find similar groups. When we have fixed a metric and a historical feature, or maybe both, we choose a test or several tests at the same time for our division. Usually, the Kolmogorov-Smirnov test, the Mann-Whitney test, and the permutation test are well suited. The Kolmogorov-Smirnov test is not used to assess the effect, but it is well suited for testing the uniformity of distributions. The Mann-Whitney test and the permutation test are often used to assess the effect, but they are also very good for testing homogeneity. And if we don't have such large sample, we can generate 10,000 or 100,000 random pairs and find such pairs where our conditions will be met. One or two tests will say that these groups look the same for some reason. For example, I split the regions into groups in the first iteration using the Mann-Whitney and Kolmogorov-Smirnov tests simultaneously for the target metric, but more on that we will discuss later. It's also important to note here that if we use many criteria and metrics by which we select, then we need to make an adjustment for multiple hypothesis testing to correct our p-value. Let's continue with the next algorithm. We select groups by cost function or similarity metric. Here we also select the target metric and or other historical features by which we want to find similar groups, choose a similarity metric, for example, L1 norm, L2 norm, scalar product, or any other. We can also compose a cost function from metrics with some parameters. Let M be set of all metrics and features, and D a set of dates. For each date for the metric M, we can average all observations in groups A and B, get a vector of dimensions dimensions D. And then we have vectors A and B, calculate, for example, the square distance between them and multiply it by some lambda coefficient. Lambda is the weight of our metric. We can do this by summing over all metrics and we get a cost function between groups A and B. Then using, for example, a genetic algorithm, greedy search, or random search, we can find such groups A and B that have the minimal or small enough value of cost function. If we do this by a random search, then there is a question, which threshold to consider for groups A and B similarity. For example, consider the following procedure. We generate 10,000 pairs, calculate the cost function for them, draw the distribution, calculate some percentile, and take some cutoff threshold. And this will be our threshold for considering groups to be similar. All the articles that talk about this or that method I will cite below. The cost function on the slide was taken from the article below. Let's go further. The next similar group selected algorithm is based on the target metric predictions. It should be noted here that we don't predict the target metric and then look at the validation period of deviation of real values from our predicted ones. Not exactly. Actually, we are predicting a metric here to get more information. We predict the target measure for the pilot period. Then we can apply our previous two algorithms using the information we got from predictions. It is important here that there should be some simple good model, for example, linear regression, and the model prediction errors should be normally distributed with the center at 0. An article about the target metric forecast is also given below. Okay, let's now move on to the last algorithm, selection of groups by the Atkinson index. It came from an article from the 2020 LinkedIn company. They use the Atkinson index just to check whether groups A and B are fair or not, according to one indicator or another. Unlike us, they had a lot of data. So we tried to implement this article in those cases when we don't have much data. Let's take a closer look at the Atkinson index, which is an economic index, an index of a social inequality. Usually they measure it by how evenly income is distributed among the population. And it also has a certain parameter, epsilon, which is responsible for how sensitive we should be to how evenly income is distributed. Should we focus on low incomes or high ones? Let's see. We have a sample of x1, xn. The sample-based formula for the Atkinson index is similar to the exponential mean of 1 minus epsilon. Having calculated such an Atkinson index for groups A and B, for example, for our target metric or any other features in the historical period, we can, in the case when we have little data, just take the difference modulus and apply some kind of heuristic. And just as before, by random search or greedy search, find those groups that will satisfy us by all parameters. By default, an epsilon of 0.5 is used. Let's now move on to the next section, how to conduct A/B test on regions. Let's try to apply some of the methods that we are now familiar with. I want to tell you about a real case that I encountered and in which it all came in handy. Why is this important? What was the task? We work in the B2B segment. We have a marketing department. It makes samples for the sales offices at MTS allocated in every region of Russia. Then each sales office calls entrepreneurs in these regions. And finally, entrepreneurs use MTS services. MTS solves the standard business task in the B2B segment: attraction, development, churn prediction. What does big data have to do with it? Big data makes a new product and it is supposed to optimize sales and marketing, and entrepreneurs will be loyal. They will buy more services, they will turn out less, and we will earn more money. But how can we verify this? The main difficulty hides in dividing regions into such similar groups according to the sales data available to MTS. We want to offer a big data product to one group and not to the other. We want to validate if big data really brings in more money and how much more. Let's take a look at what data we had. We had revenue from sales in business categories of the region and geographic regions per month over the past 2 years and the number of customers for each month. And that's all. Income has very high variance, therefore it has low sensitivity. Let's divide income on the number of companies so we get the average income per company in each month. This metric is also interpretable for the business and it has lower variance. On the plot, you can see a histogram of the received metric It's clear that it's not a normal distribution at all. Let's look at the same metric for regions in 2019. We can see that time series differ one from another. I also want to note that as an observation, it's possible to take also averaged metric of the region over several months or even 6 months. Let's also discuss how to evaluate the group selection algorithm in this problem. We fixed the algorithm for selecting similar groups during the training period, select n pairs of similar groups. Then, for each pair, we conduct an AA test on a validation sample, compare the groups according to some criterion, look at the uniformity of the p-value distribution, and evaluate the false positive errors. If the p-value is uniformly distributed, we add the effect to one of the groups for each pair on the validation sample, compare the groups according to some criterion, and evaluate the power. Why is it important to look specifically at the uniformity of the p-value distribution? When we have similar groups, in a test p-value should have uniform distribution. Let me clear it up. When we take some threshold at 0.05, we assume that we have a percentage of false positive. When we take the noise as an effect, it will also be no more than 5%. If we increase p-value to 0.1, then we assume that we will have no more than 10% false positives. And so on. If we continue to increase by a certain number of p-values, then the percentage of false positive errors will also increase by the same proportional value. This would be a function that would ideally goes 45 degrees. The only situation where this is possible is when the p-value is evenly distributed. We will always pay attention to this and therefore fix it. This will be one of our main criteria, which will tell whether we have the right algorithm for selecting similar groups, metric and criterion or not. We will also form attention to the whether or not our groups A and B diverge in time on a validation sample. In our case, this period in 3 months. So, what has worked well on our data? Kind of a spoiler, at first it did not work very well, but we fixed it with a small trick. What has worked is the Mann-Whitney criterion applied to historical data for the target metric. Groups selected by it should not show a significant difference, and also groups selected by the Kolmogorov-Smirnov test should not show a significant difference. Let's randomly search for those partitions among 10,000 or 100,000 partitions for which all the conditions are met. As you can see, I also left the heuristic for income, but there was not a real effect on it. But for requirements of the customer, it had to be left. How will we rate our pilot? With which criteria will we evaluate it on a time validation sample? We can evaluate it, for example, by the Mann-Whitney criterion and the permutation criterion. We cannot use the t-test. The distribution of our metric is not normal, but I took it for the interest. We can see that the false positive is good, 0.05%, 2.5%. Our power is as follows. In 85% of cases, we catch 7.5% of the effect by the Mann-Whitney criterion, and the permutation criterion is 8% of the effect. We can conclude that everything is correct in terms of correctness. But if we plot the distribution p-value, we can see that this distribution is not uniform, which means that the criterion is not correct. What should we do in that case? We may have three situations why this happened. Either we choose the wrong metric, or we choose the wrong algorithm for selecting similar groups, or we choose the criterion incorrectly. Let's think about the metric. Let's discuss the transformation of the Cupid metric. There have already been many great speeches about it. Below, I also gave a cool article from Booking about it. The thing is that we subtract the centered covariate multiplied by theta from our metric of interest. Under the covariate, some correlated value is implied. It is widely used to taking covariate, for example, as target metric before the A/B test. We have a very similar situation. We know how the region behaved before the pilot on average, and we know how it began to behave after. We can use this to make a combined metric. Let's use the Mann-Whitney criterion applied to Cupid transform the target metric on a validation sampling, of course. It can be seen most importantly that the distribution of p-values becomes uniform. And even when we use the Cupid conversion, our variance is greatly reduced. We are catching effect more sensitively. It's already 4.5% of the effect in 85% cases. Let's see what we get using the algorithm for selecting similar groups based on homogeneity criteria. We want the Kolmogorov-Smirnov and Mann-Whitney test say that we have the same groups based on average income attributable to the company. Also we apply a small heuristic for our business customer restrictions. By the way, it does not affect anything. By random search, we select those groups for which all the conditions are met. Consider a Cupid transformation and estimate the effect by the Mann-Whitney criterion. Let's see how the final variant worked for us in terms of homogeneity. In our example, in the group A and B for each date, we averaged all observations, and they built a plot for 2018 to 2019 for the last 3 months where we evaluated our effect. Why did I take the last 3 months? Although they have such a big leap for the new year. Because everything was complicated by the fact that it was necessary to carry out this test during for the coronavirus pandemic. And it was assumed that there would be the opposite effect, sales would fail strongly downward, but the variance would be just as high. It can be seen that during 2018, our groups behave in a similar way, albeit with a small gap. During 2019, they behave very close. Well, in the last 3 months, they are also close and repeat the structure of each other. Let's see how the Atkinson index performed. It also coped well with this task. For which metric did I use it? I tried to use the Atkinson index not for the target metric, for the target metric, and also tried to apply a Cupid transformation on them. And you can see that in all 4 cases, we have a uniform p-value distribution, so everything is correct. The most sensitive way turned out to be when we use target metric with a Cupid transformation and put the Atkinson index on the target metric. Let's look at the division of regions using the Atkinson index. We catch about the same effect, and you can see that the time series behave in a rather similar way. In fact, I cannot show what exactly this gap between time series is, but this is a very small gap. We see that although a little of the group dispersed in front of the pilot, they still generally repeat each other. Okay, now let's move on to the second case in which the selection of similar groups turned out to be very urgent. This is the conduct of CRM campaign in the B2B segment. I will tell you about the process. Big data gives some samples to marketing. Marketing is carried out by CRM campaign and then managers in the sales office negotiate with entrepreneurs, make appointments for them, and try to sell some services. It seems that the task is simple, but there is a number of limitations that complicate everything. For example, a campaign lasts 3 months. That is, a manager can negotiate with an entrepreneur for a very, very long time. The business customer is only interested in the money metric. That is, these are average charges and the first charges that entrepreneurs make. The sample size is always less than 1000 because we don't have many entrepreneurs and we cannot sacrifice them much. Also, the money metrics assessed by the customer has a high variance. We cannot switch to another metric at the request of the customer. Even within a single region, for example, Moscow is the capital of Russia, or some even smaller region, the groups turn out to be very uneven in all important indicators. For example, by indicators of accrual. Also, there are additional restrictions from the customer so that the averages don't differ by a very large number. This also makes its own adjustments. Let's apply the Atkinson index. Let's see what we get. Here, the Atkinson index looks very logical. We work with money metrics, with accruals. They are very similar to income. We have accruals for the month before last, for the last month, and we can calculate the Atkinson index for groups A and B according to one metric and according to another, through an heuristic for the models of the differences, and using random search for those groups for which all the conditions are met. In the end, we also add restrictions from the customer. As you can see on the right, p-value is distributed evenly over the accruals that were for the next month and for the average charges that were in the following months. That is, we counted the Atkinson index for the month before last, averaging them over the last month, and evaluated them after that. We looked at the accruals for the next month and for the following months online. The index worked well over here too. Okay, let's summarize now. What is important when we have a small data sample and we have to estimate the money effect? We need to choose the correct money metric or move on to another desirable, interpretable metric with lower variance. Also, we need to reduce the variance as much as possible. Next, we need to select a criterion by which we can evaluate, in this case, the effect of A/B testing of a new tested feature. Then comes a very important part. We must choose an algorithm for selecting similar A and B groups, evaluate it and make sure it's correct, evaluate the distribution of p-value first so that it is uniform, and do it at different time period on the postponed part of the validation set. Also see if our groups don't diverge on delayed sample and carefully use methods to increase the sensitivity of the test. Not all of them can be used when we are dealing with small samples and money metrics. What did I want to say in general by this talk? It does not matter what size the samples has. It does not matter in which format the data is. That is, even if it is an Excel spreadsheet, if we have a small chain of stories or a small size segment, then even in this case, although with certain difficulties, it is impossible and necessary to conduct a correct A/B test to assess the money effect and make the right conclusions. Thank you all for your attention.